Have you ever wondered how exactly Snapchat keeps your selfies from being stolen and your pictures spread across the internet? Before sending your pictures, Snapchat encrypts the image or hides exactly what the image looks like from everyone except the sender and the receiver. Even if someone managed to download that image without the correct information, called a key, needed to reverse the image, they would have very little chance of ever seeing the clear image you sent. My name is Kayla Robb, and I'm a junior mathematics major. In the last 2 years, I've worked under the mentorship of Dr. Teresa Jorgensen to explore current fields of research in cryptography, including the growing interest in image encryption as it relates to chaotic keys and fractals. Encryption uses a general mechanism with a specific hidden bit of information, the key, which keeps everyone except the intended recipient, and sometimes the sender, from reading the encrypted message. To do this, cryptographers want to make the encrypted image as unpredictable as possible for people who do not know how to undo the process that made the image random. However, they also want to be able to undo the encryption in order to recover the original image when needed. When using a chaotic image as the key, the encryption can use the inherent randomness of the key to add an extra layer of unpredictability in the encrypted image. Also, since chaotic images only need a few parameters to create a great deal of unpredictability, sharing the key to reverse the encryption is relatively easy. Instead of sending an entire image, people sending an encrypted image can also send a few numbers along with the encrypted image, and the receiver can regenerate the chaotic image and undo the encryption. One common chaotic image is a fractal. A fractal is a geometric object that on first glance does not seem to be like any geometric object you've ever seen. A fractal is characterized by infinite complexity. The closer you zoom in on one part of the fractal, the more detailed it is. Self-similarity. Small parts of the fractal will represent the whole fractal. Irregularity. A fractal is so detailed and complicated it cannot be described well by normal Euclidean dimension. To discuss fractal dimension, mathematicians use Hausdorff dimension, which allows us to capture the infinite irregularity of fractals. I hypothesized that a fractal with higher Hausdorff dimension would lead to a more random and thus more secure encryption when that fractal is used as the key for an image encryption system. To test this, I created a fractal-keyed encryption system, which could either generate a specific type of fractal during runtime, or could use an already generated fractal image as the key. I then encrypted and decrypted 3 test images with 20 different fractals, of which 16 were generated and 4 were pre-generated fractals. Based on encouraging initial results, I decided to take another sample of an additional 3 images and encrypt them with the same 20 fractals, resulting in around 120 samples and 6 distinct populations. After encrypting and decrypting the images, I used 6 common security metrics to gather information about how similar the images were to an ideally encrypted image, one that is totally random and has no deterministic properties. Based on the information gathered from these metrics, I discovered there is a statistically significant correlation between the Hausdorff dimension of the fractal used as an encryption key and the randomness of the resultant encrypted image. Correlation between dimension and entropy, a measure of the predictability in an image, averaged around -0.65 among the sample populations, showing that a higher dimension of the fractal key meant less predictability in the resultant image. Correlation between dimension and deviation from identity, a measure of deviation from the ideally encrypted image, averaged at 0.52 for the sample populations, demonstrating that a higher dimension resulted in less deviation from identity. Based on this, cryptographers utilizing fractal keys as keys for their encryption systems should prefer higher dimension fractals, since these are not more difficult to generate and result in better, more encrypted images.